I'm giving you the image of where I am, a nice sunrise here in my city with a lot of mist.
Oh, great. Yeah.
Good afternoon, everyone. Welcome back. The session chair for today will be, for this session, will be Dr. Sukanta Das. I request him to chair the session, please.
Okay. Good afternoon to everyone. We are starting our post-lunch session. And Pedro, good afternoon from India. And good morning. It's early morning from your side. You know, you are taking a lot of travel. Anyway, our first speaker is Pedro. Pedro is a professor at Mackenzie Presbiteriana University in Sao Paulo, Brazil. He's an active researcher in cell automata, automata networks, evolutionary computations, and multi-agent systems. He was IFIP president. He was a president for 2 or 3 years, and he's an active member of IFIP group, as well as he's one of the organizers of Automata. He has several roles, and I must say that from the very beginning, Pedro was Pedro was supporter of ASCAT and our Automata India group, and this time Pedro acted as general co-chair of this conference. And from very beginning, and on every aspect, he suggested us, he gave opinion and many things. We get support from Pedro, so we are very grateful to Pedro. And this talk, this time is for Pedro, and he will present this talk, and the talk title is solving the parity problem in automata networks. So over to you, Pedro.
Thank you, Sukanta, for the nice introduction, and I'm very glad to be with you. Well, I was hoping to be actually in person with you, but it didn't work out. This time it was perfect for me because it's a long week break due to the carnival, the official Brazilian carnival. So it's a long break. So, but it didn't work out, and since I didn't have the opportunity to be in the opening of this event, I would like to thank Sukanta and Supriti for all the support, my fellow co-chairs, and I must say that I was very impressed by the level of organization, the strictness of the reviewing process and everything. So congratulations to all of you who have been managing this event, and ASCAT is a reality these days with this fourth edition. So thank you very much, and okay, let's go. I will share my screen. Can you see it?
Yeah.
Can you see? Yeah.
Yeah,
okay.
We can see.
Okay, so can you see my cursor moving? The cursor over the image.
Yeah. Yes.
Yeah. Okay. Yeah. So I'm going to talk about this parity problem, which is a well-known benchmark problem that goes back to the beginnings of neural networks, and in terms of automata networks, and in particular cellular automata, it's been on for quite a while. And together with the density problem, these are the two most well-known benchmark problems to probe the ability of automata networks to compute, to do something that we want them to do. So what I'm going to do is review some recent works that I've been involved with. There's some older stuff as well, but so this is the way we're going. First, I will define the problem, and then I will go on different approaches to tackle to get the solution, and with some concluding remarks. Okay. This is the standard formulation of the problem that was put forward in the context of cellular automata, actually. So you have a binary. Every line here has one defining feature of the problem. So it's a binary, one-dimensional cellular automaton rule to determine the parity of ones in an arbitrary initial configuration with odd size, odd length, in periodic modules, which means the configurations are cyclic. And you want to determine the parity of ones in terms of getting the rule to converge to the fixed point of all ones if the parity of one is odd, and convergence to the fixed point of zeros if the parity is even, which means convergence to the sum mod. Hello?
Yeah, we can hear you. All right.
Okay, because I'm hearing, maybe I'm getting some echo. So this is the problem. So this is in its simplest and standard form. You have a one-dimensional cellular automata binary. You want the convergence to go to the sum modulo 2 of the sum of the states in an arbitrary initial cyclic configuration. Okay. So let me talk then a little bit about solution with the single rule. So in 2013, I was working with these two. Well, I should say something. All the works I'm going to mention here, they've been done with various people and students and so on. So this will be apparent as we go forward. So in this case, I was working with these two Canadian researchers, Heather Betzel and Paulo Flocchini, and we published this solution. And you can see here that I'm putting solution in between quotes. And in this paper, we showed that the problem cannot be solved with a single rule with radius 2. It means every cell seeing two guys in each side, right? So this is a solution. This was supposed to be a solution with radius 4. And it looked like this. On the left-hand side, I have the convergence to time 0 is at the top. Time 0 at the top, time is flowing downward. And the convergence here is to the odd parity of the initial configuration. Here, it's the even parity. So this is the kind of temporal evolution that we get with this rule. we use the word accordion, the musical instrument, because it goes on this process of extending and compressing the blocks. So we published this. This was in 2013, but 1 year later or a bit more, we found there was a bug in this project, in this rule. And it was, I had no idea how this happened, but for a specific configuration size 13, it wouldn't converge. We then worked out a solution. And now you can see that I'm putting solution with a question mark here. And this was, there's another name here, Martins was a student of mine. So we worked out the solution. The previous rule, we called it BFO. So to this rule, we called it BFOM, like modified. And why I'm adding this question mark here? It is because although we made a supposed fix to the original rule, we couldn't get a proof for it. So we wrote this paper in 2016, and it was kept in the drawer because we didn't manage to get a solution, but we submitted this rule to all odd size configurations up to 35. So I believe this is a solution, but we still don't have a proof for it. And what we did, actually, this is a characterization of the original BFO rule. I'm representing here only a generalized version of the active transition. So we can see here, for instance, the zeros in boldface. So and the star is a don't care. So every line here, this T1 represents a set of rules which flip the central bit of the configuration, of the neighborhood, actually, of the. So the fix we did from BFO to BFOM was instantiating these two active state transitions, T3 and T4, like this. So it became more spatialized, and this was crafted to solve that particular problem. And we believe this will solve the problem. But we still no from one moment onwards, we just kept this in the drawer and waiting for another opportunity. But this is the situation right now. More recently, and some of you, I think Sukanta was last year in Automata. So he probably is aware of this. Barbara Vonik and Anna Nenka from Poland and Bernarda Betts from Belgium. We worked together. They knew about the problem with the BFOM. I had shared the situation of this bug with various people, Nazim Fates, and other people who were also interested in the problem. And I even shared the original BFOM, the supposedly correct version of BFO with them, and so on. And we started working together in a possible solution. And this is what we came up with. And this is in archive since the end of last year, and it's submitted. So we're waiting for the outcome of the reviewing process. So here we did a different correction of the BFO. If you can see this T7 and T8, they were reflected, on the corrected version for T7 and T8 are reflected. It was a very simple way to correct the version, and but the proof became completely different. So we had to come up with a very different way to get the proof. So, but this is the situation right now. So summing up this situation with one rule, we know now that there is a solution with radius 4, possibly 2 because of the solution we have computational support, but not a proof, but possibly 2. There's no solution with radius 2. And last year also, Ananenka, Barbara, and Bernard, they published a paper that there's no solution with asymmetric neighborhood of 2.5. And it's still open with radius 3 and radius 3.5. So this is the current situation. Okay. In the past, there were also some attempts to solve the problem by changing the rule along the time. So the first solution, it's a very, very old one, and it relies on elementary cellular automata using these rules. And there is a defined way to change the rule from one to the other. This was the original solution. Some years later, together with a student, we greatly simplified the solution in terms of the number of changes and the number of time steps that each rule would have to go through in order to get the solution. There was a generalization of this. Basically, the same guys who proposed the original solution, and there was this generalization for mod 3. So it's 2 convergences, right? It's a convergence of the number of ones mod n equals 0 or mod n different of 0. And later on, we managed to simplify, to generalize this for arbitrary mod n. I'm saying this because we will mention at the beginning another generalization that we've just come up with, but it's a different kind of generalization. Here we have just two convergences, right? According to the property of the number of ones in the initial configuration. So basically, as far as I know, this is the situation with the changing rules along the time. And it's interesting that, with a single rule, we know we need at least radius 4, but if you allow changing the rule along the time, it suffices to have elementary cellular automata, which is very nice. There are solutions also. There's a bunch of solutions with this scheme, also for the density problem. But you know, it's nice to have elementary cellular automata solving the problem. Here, it's another approach. You may know that the elementary cellular automata rule 150 is the local parity rule of the space. Okay. So in this solution, we rely on asynchronous. The two previous solutions were synchronous updates. Here, we are going to use an asynchronous deterministic update of the kind, the block sequential. The general, this was published in 2019 with a former student and now a colleague. And basically, block sequential updates, just to remind you, deterministic block sequential updates, you get a partition of the configuration and you assign a priority to each block of the partition for the update. So here we use a very simple block sequential update, which is we first update the even positions and then the odd positions. So the entire, there are just two blocks. First update with elementary rule 150, all the even positions, and then the odd positions, even positions, odd positions, and so on. And this is the kind of pattern that we get. I like very much this because you solve the global parity problem with the local parity of the elementary space and doing the block, the two blocks are the even and the odd. So everything is kind of parity, right? So the solutions here get there are two solutions depending on the size. So I'm calling the notation here. L is the length of the configuration, and there are two cases when L is equal 4K plus 1, and a second case 4K plus 3. Sorry. You can see here in this image that there is this straight black line here from this point downward. And the way this thing works is like this. I'm using here as example a size 17 with K equals 4. And this is time 0, this is the central cell. And what happens is that after some time, that's well determined, the central cell converges to the parity. After some time, the configuration becomes symmetrized. You can see here one is the mirror of the other. So at this point, we have the central cell converged, and the two and the rest of the configuration mirrored. From this point onward, then there is the convergence to the entire lattice. A similar thing happens with this other case for K plus 3. Again, the convergence of the configuration of the central cell with the parity of the initial configuration, then the symmetrization, and then the convergence. So it's basically the two cases are very similar, kind of identical. Just the timing of each of these stages that changes, but the process is the same. I'm sorry, maybe I'm speaking too loud. It turns out that this asynchronous solution that I just showed, it can be regarded, there is an equivalent to it in terms of a non-homogeneous CA in synchronous mode. And here I'm exemplifying six networks where in black, the nodes in black, they are the local rule of the elementary space, radius 1, which is 150. And in red, the local rule, the local parity rule of radius 2. So there is a way to arrange the local parity rules with radius 1 and radius 2 that gets the same solution, but synchronously. So this is nice. Also, it's very interesting. I'm going to mention now another solution, again with rule 150, but in a synchronous case, synchronous kind of update, but in a different kind of graph. Here, in this case, it's a standard. It's a standard cellular automaton type of graph, a circular graph. And what we obtain with using a more flexible arrangement of the rules is the possibility of solving the problem synchronously, but once again with elementary rule 150. So this was published in 2022 with another student and another former student. This is one possible graph. Okay, so I'm just exemplifying here. I'm arranging. I named the nodes with numbers, and I'm aligning them here and performing the operations. So times. So it's a different kind of graph. There will be real examples as follows. So what we have here then is a rule vector, and I'm representing here a rule vector. Each F is the rule number, and N, the corresponding capital N, is the connection of this position. So I'm saying here, well, I have an example here. For instance, in this rule vector for L equals 7, rule 150 will connect to the cell. Well, this is position 1. Okay, this is position 1. So in position 1, we have rule 150. In fact, all the positions will have the same rule, which is 150. And I'm saying here that in this position, the rule will connect to the position -1, which means on the other side of the configuration, and 3 positions to the right. So the number, and there is also a self loop, which is represented by this 0. So in the simplified notation, we would have a solution like this, where every rule then is 150. There is a self loop to each one, and the specification of the neighborhood connection pattern is relative to the position. Okay, so it's just for you to get a feeling about how things work. And when we were trying to come up with the solution, we did a lot of computational experiments, and we could find different kinds of solutions, but the possibility to generalize one solution to arbitrary configuration sizes came up when we sticked to graphs that would have some symmetry, which is reflected here in the neighborhood connection pattern of these two solutions. You see there is a symmetry by mirroring on the first half and the second half of the graph. So this is one possible solution here for L equals 7. These are the relative positions, and in blue, I'm representing the left-hand connection of the position. In red, the right hand, and these are the relative positions and the absolute positions. And so you have this kind of graph where the arrows in blue then are associated to the left hand, and the arrows in red correspond to the information coming from the right. Okay, we can skip this. There's a way to construct for a given configuration size. There are four kinds of ways to construct the rule vector, but this is detail. Once again, there are two cases, right? For k plus 1 and for k plus 3. And this is the kind of graph that we get. This is for the case for k plus 1 and for k plus 3. It's not trivial to see the well, in these small cases of configurations, it's easy to visualize the symmetry that we get in the graphs. So this was well, for L13 it's more difficult, but in general you can visualize the symmetry. And this was key when we were exploring the space of possible graphs that would give us a solution. And this is the kind of pattern which is similar to some extent to what we got in the previous case, but the process is very different. It's related, but as you see, it's different. So I'm representing here the case for k plus 1, k equals 6. And the first thing that happens is the symmetrization of the configuration, just like before, and the convergence of the central cell in an even position to the parity of the initial configuration. So this is also what happens in the previous case. And now the situation gets more intricate. because first, the central cell, the parity of the central cell extends to the nearest neighbors of the center at odd positions in 2 time steps. It requires 2 time steps for this central cell to pass on to the next near neighbor in odd positions. Then the remaining odd positions converge at every 2 time steps. And finally, the remaining even positions get the parity of the central cell. So it's a more bit more intricate process. This is for 4K plus 1. In the case of 4K plus 3, the first step is the same, the symmetrization and convergence of the central cell to the parity of the initial configuration. But then the situation changes. The next phase, the end positions converge in 1 time step. This is very different from what we saw in the previous slide. And then from then on, the odd positions in 2 time steps converge to the next neighbor, and only then the process carries on converging to the odd positions. And finally, the remaining convergence at even positions every 2 time steps. So all these processes, they have some relation, but they're not the same, right? So there are differences. Okay, from this case I've just showed you, we then realized computationally that that was just one possible solution in a big family of solutions. So we then generalized that previous solutions where in the rule vector there was only rule 150. Now we can have also two other elementary rules, which are the shifts. 170, which is the shift left, and 240, which is the shift right. So there is a very elaborate way to assign these rules in the rule vector. So to the end, to the point that you have 2 extremes. In one extreme is the previous solution where only one rule 150 is assigned, and in the other extreme there is only one occurrence of rule 150 in the center of the configurations, and all the others are rules 170 and 240. So this is the big family, and there is this combinatorics of assigning the 3 of them, except you don't have a choice in the central cell, which is always 150. But in the rest of the configuration, there is a whole combinatoric possibilities of assigning these 3 rules, which is what gives us these huge possibilities of solutions. One thing that changes here is that in the previous cases we would have in the previous solutions we would have 2 cases, but now we have 4 cases according to configuration size. So 8j plus 1, 8j plus 3, plus 5, and plus 7. So this has to be crafted in 4 different kinds of situations according. And the idea here is the notion of rule blocks. Okay, I'm not. I'm just carrying across the idea of what happened. So we have 3 kinds of rule blocks, which we denote BM, B capital M over 2. M, big M, is the number of BM blocks. So there is this notion of some blocks, but there is this special one that deserves an attention because it's different. And there is the 2 types of B blocks, end blocks. So we have 2 types of these BM blocks, 4 types of these central blocks, and 2 types of these end blocks. And they are rule blocks. So they have different kind of rules that you can have in them. And each one of the 4 cases is defined in terms of the number of blocks of each type that you need. Just to give you an example, the 2 BM blocks are these. This one is 4 rules 150. And the other block is 170 to 40, 170 to 40. For L, AJ plus 5 and AJ plus 7, these are the central blocks. There are 4 types of central blocks. And the end blocks, which appear in AJ plus 3 and AJ plus 7, these are the 2 kinds of blocks. So this is a general scheme of rule vector that you get. You see in red, in green, the end blocks. In red, we have the BM over 2 blocks. You can see here, right? And in blue, we have in the case of B1, but there could be, depending on the size, there could be a B1, B2, and etc. And one thing to be noticed is that the blocks are partitioned when allocating them in the rule vector. So, for instance, you can see here the end block. The end block, we see that there are 2 rules in the end block, but I'm saying here that I'm breaking the block in 2, and the first rule comes in the leftmost extreme, and the second of the block comes in the rightmost extreme. So all the blocks, when allocated to the rule vector, they are actually broken in 2 parts, and everyone goes in one part of the okay, you don't have to go in. So this is the general allocation. These are just actual examples. It's not important. So we didn't prove that these would represent a solution. But as you can see here in a sample of sample evolutions of all the 4 cases, they are a bit different, but they look like very much the kind of solution we had for the previous case, in which all the rules in the rule vector would be just 150, right? So we strongly believe that the same kind of technique that we used in the previous solution could be used here. And in order to support our claim, we did exhaustive experiments for all network sizes up to size 23, and did a sample of in larger sizes. Oops. For larger sizes of these 4 sizes here, from 40 something, 120 something, 200 something, 400 something. And for each case, we did a sample with 20,000 initial configurations in the two extreme solutions that I mentioned, the one with only 150s and the other with just 150 in the center, and the others and the other rules 170 and 240. So the paper is very complicated in terms of showing these constructions of the blocks and everything. So, but we strongly believe that the same kind of proof could be used. And just to mention one thing here, I'm taking 4 solutions for configuration size 9, 2, 4, 6, yes, for 9, and we see that the solutions are actually different. This is the same initial configuration for being submitted to the 4 solutions, and we see that they are different, but in this case, solution 2 and solution 3 are mirror reflected to each other, and there is this suggests that maybe it's possible to shorten to come up with a more generalized way accounting for these symmetries. But in general, we see if we take this one or this one and this one, the process of convergence is very different, which means that they are kind of different algorithms being executed. So some concluding remarks. Parity determination is certainly easier than density, and one reason to think about this is that parity can be handled in terms of general automata theory with a finite automaton. But density, you need at least a push-down automaton. So this reflects in the possibility of solving the problem. And the existence of n complexity solution depends on the problem formulation. If we define a problem in a way we cannot solve it, maybe that formulation is too strict. So all these kinds of solutions tell us that you should maybe formulate the problem in another way. So this is good news, right? In terms of getting automata networks to do something, because maybe you get a negative result from a formulation, but that's not the end, because you can change the formulation and get a solution. Using fixed boundary is intuitively very much simpler than cyclic configurations. And as I mentioned, the previous solution possibly accounting for that symmetries that we see that I hinted at, it could lead to a simplification of the possible solutions in the last approach. And well, parity and density determination are examples of problems solved by distributed consensus, right? Because we have, it's a direct consequence of the way we are formulating the problem, which leads to the convergence of the entire configuration. It's a consensus, and it's distributed because every node in the network only operates locally. And I'll just very quickly mention the further generalization, which something we are calling the K-parity problem. This is also in archive, and it's a work with Pacon Perrotin. He was a postdoc from Aix-Marseille in France, who came to my lab last year. And it's submitted, it's currently submitted. It's one step for final approval, we hope. So it's a generalization to K-area configurations. So we now have states from 0 to K minus 1. And the K-parity problem is the convergence to the sum modulo K. It's a synchronous solution to convergence sum modulo K of the initial configuration. And so if we are then in the case K equals 3, then we'll have 3 different configurations, which is different from that generalization that I mentioned in the beginning of the talk, when changing rules in which the convergence would remain just to all zeros or all ones. Now we have a convergence to K possible fixed points. And so this is a solution with K equals 2, which is the parity, the parity problem. So it's basically, there is this notion of a central cell, and you keep adding any way you want cliques, strongly connected components of size 3. So if we start here, you can keep adding these cliques, and all the local rule is the sum modulo 2 in the case. So for K equals 3, then we would have this kind of situation. And it's interesting that this is just one possibility of the network. So you can add these cliques any way you want. Well, you know, the convergence goes on from the central cell. The notion of central cell, it goes on spreading. So if you have a graph with diameter p, with a certain diameter, after p time steps, the whole network converges. So I'll stop here. Thank you very much for your attention. I think I'm inside my time.
Thank you so much, Pedro. Very nice talk. Indeed, the first part of the talk, the BF rule, as I recall in Automata, Barbara presented this one, and quite interesting talk. Yeah, thank you. So the time for questions, question from audience. So, Pedro, I have one question. While you are using block sequential update, right? And the question is, how do you decide the size of block?
Well, in the particular solution we used, it's the size is not an issue because it's first you update the even positions and then the odd positions, even positions, odd positions, and you go like this. In other context, then this could be an issue because there's a huge number of possibilities of partitions that you can do in the configuration. But in this case, it's very simple. It's just, even odd, even odd, even odd. So then it might be possible to come up with a different solution with another rule, with a different kind of block or family of blocks. But this wasn't an issue for us.
Okay, good. And another point, so the last regarding the K parity problem, so
Yep.
you are finding, say, K fixed points, right? Now,
Right.
for the ECA rules, is it possible to have get any solution for the K parity
Sorry,
problem? If
is
I
it
use the
possible to do
ECA
what?
rules, with the ECA rules, ECA, elementary cell automata.
Um, well, I suspect that, well, for K equals 2, it's rule 150, right?
Right.
For K equals 2, it's rule 150. If you're asking whether we could solve the K parity, the generalized version of the K parity with a different rule, I think it's possible. But then you would have to come up with a different kind of graph. And, this is very dependent on the graphs. We can see this in the last solution of the K parity, and even in the cases that we would have the non-circulant graphs with rule 150, right? So I believe other K-area rules could solve the problem with a different graph, maybe even more efficiently, but we don't know. We're happy with this solution. The network is very symmetrical in a sense because you keep adding clicks and you have this flexibility of adding the clicks wherever you want. And so it's a nice homogeneous network.
Okay, so it may be tried with non-homogeneous C also, especially with ECA rules and K parity problem. Maybe someone may be interested to address this problem with non-homogeneous CA. I mean, this non-uniform CA.
Yeah.
Okay. Well, any other question? Okay, yeah. Shupriti, please.
Hello, Professor Pedro. How are you?
Hello, Shupriti. Nice to meet you.
Hello.
Again.
Yes, I have seen that you have used CA with radius 4. That means it is 9 neighborhood CA with one-dimensional 9 neighborhood CA. The rule space is huge. So my question is, how are you handling this such a big, large rule space?
Every time we try to design a CA that you wanted to do something previously defined, it's a mix of science and art, right? So you have some feeling and you try to design something that would work in a certain set of configurations, and then you go on adjusting, doing computational experiments, and so on. There's no way to circumvent this problem. In the past, I have used a lot of evolutionary computation to search the space. Right? So this is actually many people that who had tried to come up with a rule, searching evolutionary computation has been clearly the best way to do it. And I've done quite a lot of research in this, especially for the DCT, which is a much harder problem, right? And has no solution actually with one rule. And it's like that, Supriti. It's you try and test and push it here and push it there, and at the end, there are lots of computational experiments to get convinced, and then the proof to actually be totally convinced.
Yes. Okay. Okay. Right. Thank you, sir.
Thank you.
Any other question? Maybe no. Thank you once again, Pedro, taking so much travel. It's early morning to you.
It was a pleasure. Thank you so much for all of you.
Thank you. But we had some presentation, we had some memento for the speakers, but sorry, we can't present you online. So please accept our gratitude. Okay. Thank you. Thank you once again.
I understand. Thank you very much. Bye-bye.
Bye.
With that, we'll now take a short break till 3:45. Please enjoy your refreshments and reassemble back by 3:45.